Hi folks, Mrs. Gates here. Today we are going to continue our study of energy. We have already talked about the conservation of energy, and today we are going to look at various types of energy, coming up with an equation for each so that we can use them to help us solve puzzles. Let's go ahead and get started. Let's consider an example to review the conservation of energy, the forms of energy, and how we used our pie chart diagrams. In this example, a ball is launched straight up into the air and then falls back down to the ground. Let's consider what forms of energy it has at each of the 5 labeled points along its trajectory. We'll start with point A. This is at the ground level just after launch. Since its height is 0 and is moving its fastest, that means that all of its energy at this point is kinetic energy. As the ball moves upwards, it slows down and its kinetic energy is constantly transforming into gravitational potential energy. By the time it gets to point B, it has over half of the energy as gravitational potential and only a small amount of kinetic energy left. And when it gets to point C, the very top of its trajectory, its velocity is equal to 0 for just an instant. At that instant, its energy is completely gravitational potential. But then it begins to fall back down. And as it does so, the gravitational energy is transforming back into kinetic energy. When it gets to point B, the pie chart looks something like this. And when it gets to point E, all of the energy has transformed back into kinetic energy. If you compare the pies for point B and point D, on the way up and on the way down, they're similar in that they both have both forms of energy, kinetic and gravitational potential. But because point B is higher, it has more gravitational energy than it did at point D. And because it will be going faster at point D, it has more kinetic energy at point D than it did at point B. The forms of energy that we will look at equations for here are gravitational potential energy, kinetic energy, spring or elastic potential energy, and the energy dissipated by friction. Let's look at them individually. We'll start with gravitational potential energy. The amount of gravitational potential energy that something has depends on 3 things: how much mass the object has, how high the object is, and how strong the gravitational field is where the object is located. On the surface of the Earth, the gravitational field strength is your favorite number, 9.8 meters per second squared. But at other places in the solar system, for example, the surface of the moon, the gravitational field strength would be less. On the moon, G is only equal to 1.67. As we look at the gravitational potential energy, the equation that tells us how much gravitational potential energy something has is shown here. Mass times the gravitational field strength times the height, mgh. The symbol that we use for potential energy is the capital letter U. The subscript G denotes that we are talking about gravitational potential energy. Let's look at an example. Here we have Wile E. Coyote with a mass of 22 kilograms. At this point, he is 35 meters above the ground. How much gravitational potential energy does he have right now? Take a moment, pause the video, and come up with your answer. Using our equation, mgh, we plug in the values we have for mass, 22 kilograms, gravitational field strength, 9.8 meters per second squared, and height, 35 meters. Multiplying these together gives us 7,546 kilograms meters squared per second squared. Now, the unit on that gravitational potential energy is kind of an unwieldy unit. In physics, we give that unit a special name, just like we call a kilogram meter per second squared a Newton. This unit, a kilogram meter squared per second squared, is called a joule, abbreviated with a capital letter J. Now let's talk about kinetic energy. The kinetic energy of an object depends on the object's mass and how fast it's going, or its velocity. The equation that describes something's kinetic energy is this: EK equals 1/2 mv squared. Let's consider the example here to practice our equation for kinetic energy. Roadrunner has a mass of 12 kilograms. How much kinetic energy does he have when he is running at 8 meters per second? Pause the video, calculate your answer, and then resume to check your work. Using our equation for kinetic energy, 1/2 mv squared, we plug in 12 kilograms for the mass and 8 meters per second for the velocity. That gives us a total of 384 joules of energy for Roadrunner as he is racing across the desert. Let's consider spring or elastic potential energy next. In order to understand the equation for elastic potential energy, we need to understand some properties of springs. Consider the diagram shown here. All 5 springs are supporting the same amount of mass. What's different about them? The difference between these springs can be described by their spring constant. The fact that the red spring stretches much more than the green spring when the same weight is applied to it means that the red spring has a much lower spring constant. You can think of the spring constant of a spring being the stretchiness. It is the force required to stretch a spring 1 meter. So when we consider spring or elastic potential energy, the amount of elastic potential energy that something is storing depends on 2 things: the spring constant, or the strength of the spring, and the amount that that object or spring is stretched or compressed. The equation that relates these variables is shown here. Since it is a potential energy, we again use the capital letter U. The subscript SP stands for spring, and the spring energy is equal to 1/2 kx squared. K is our spring constant, and x is the amount that our object has been stretched or compressed. Let's try an example. A spring with a spring constant of 200 newtons per meter is compressed 0.3 meters. How much energy will it be storing? Take a moment, pause the video, and work out your answer. Using our equation for spring potential energy, 1/2 kx squared, we plug in 200 newtons per meter for our spring constant and 0.3 meters as our amount of compression. Calculating this, we get that the spring energy stored in this spring is 9 joules. The last type of energy that we will look at here is energy dissipated due to friction. When we have friction that is dissipating the energy in the system, it does not mean that the energy is disappearing. Energy is conserved. It does mean that some of the energy that our objects used to have has been converted into other forms, mostly into heat. The amount of energy that will be dissipated due to friction depends on 2 things. It depends on how big the force of friction is and how far something has been sliding. In order to calculate the energy dissipated to friction, we simply multiply the force of friction by the distance of the slide. As an example, let's consider our friend Roadrunner. We know he was running initially at a speed of 8 meters per second, and that he was sliding to a stop over a distance of 4 meters. See if you can use the information here and our equation for dissipated energy in order to find the average force of friction between Roadrunner's feet and the ground. Pause the video and take a moment. In this situation, we have Roadrunner's kinetic energy dissipating as he slides. All of his initial kinetic energy was dissipated due to friction. That means we can set the initial amount of kinetic energy equal to the dissipated energy. Using the equations we have just discussed, that means that 1/2 mv squared equals the force of friction multiplied by the slide distance. Now we can begin to plug in the values we know. 1/2 of 12 kilograms times 8 meters per second squared will be equal to the force of friction multiplied by 4 meters. This tells us that the average force of friction between Roadrunner's feet and the ground was 96 newtons. As a review, here are the 4 equations of energy we have discussed. Let's consider the examples shown here to see how the equations of energy can combine with the conservation of energy to be a powerful problem-solving tool. In this case, we have a 2-kilogram block sliding down a frictionless plane. At point A, at the top of the ramp, it has a height of 10 meters. At point B, its height is 6 meters, and at point C, the block has reached the bottom of the ramp. If we consider what types of energy the block has in each case, we can draw some pie chart diagrams that look like this. At point A, all of the energy is gravitational potential energy. At point B, some is gravitational energy, and some energy is kinetic energy. And by the time the block gets to point C, all of the energy has been transformed from gravitational into kinetic. Since there is no friction, no energy is dissipated. The conservation of energy tells us that the total amount of energy in each of these cases will be exactly the same. That means we can write an equation that looks like this. The gravitational energy at point A will be equal to the gravitational energy at point B plus the kinetic energy at point B. And that will also be equal to the kinetic energy at point C. To find the total energy of our system, we can use any one of these 3 expressions. Since we know the most about point A, we will start there to calculate the total energy. At point A, we have our mass of 2 kilograms, our gravitational field strength of 9.8, and a height of 10 meters. That means that the gravitational potential energy at point A is 196 joules. That is the total energy of our system. Knowing this total energy of 196 newtons can help us find out about other points on the block's path. For example, if we know that the total energy is 196 newtons, we can say that will be equal to the energy at point B, which we know is partly kinetic energy and partly gravitational potential energy. Simplifying this equation, we have 196 equals v squared plus 117.6. Subtracting 117 18.6 from both sides gives us that V squared will be equal to 78.4, and taking the square root gives us a velocity of 8.85 meters per second. Knowing the total energy at point A helped us find the velocity at point B. Pause the video and see if you can use a similar method to find the speed of the block as it reaches the bottom when the height is equal to 0. At point C, all 196 joules of energy are kinetic energy. That means we can set 196 equal to 1/2 of 2 kilograms times V squared. 1/2 of 2 is 1, which means that V squared is equal to 196. Taking the square root of both sides shows us that the velocity of our block at the bottom of the ramp will be 14 meters per second. As you can see, the equations of energy combined with the conservation of energy can be powerful tools in helping to solve problems. We will see more of this, but for now, have a great day and happy physicsing.